going to go ahead and turn it on. And it's reading in Fahrenheit here. It gives you a finer scale. So Fahrenheit is gives you a little bit more information than Celsius when you're reading the digital display. And this thermocouple tip is sensitive to the air temperature. Now we're going to put it in a coffee cup here that has some water in it. And we'll measure the temperature of the water. And it looks like it's working. One thing, if you're ever using these an apparatus like this, the thermocouple has to be making good contact. See, I'm wiggling it around in here. It has to make good electrical contact. And so we're getting a slightly different temperature reading, a little bit of experimental technique. So let's go ahead and start the experiment. What we're going to do is first make a water bath here. I've emptied the water into this dish, and it's sitting there at 71 Fahrenheit. Now, our apparatus is the coffee cup with some coffee in it. So let's add some heat. I happen to have a little thermal addition device over here. And we'll run the microwave for 22 seconds. Get this thing heated up. It's nice hot coffee at the end of that. It's about a quarter of a cup, I'd say, or a quarter of the cup full. We're not going to be real specific about the amounts here. We're going to just look at the process in terms of its equilibrium. So now we have heated up coffee, and the experiment is going to go like this. We're going to put this in the water bath and then measure the time dependence of the temperature with our thermocouple. So there's some hot coffee in here. How hot do you think this coffee is? This is pretty good drinking coffee, and it pops up to heating up. The thermocouple is equilibrating with the coffee now. And let's wiggle this around a little bit and see, make sure we're getting you can see if it's not making good contact, then you don't see the right temperature reading. Having a little bit of difficulty. Here we go. Let's see if I can get this thing to... Yeah, there you go. So we have two things. We have the temperature reading in Fahrenheit, and we have the clock in the background, so we can see as time passes what the temperature is doing as a function of time. So now we're at 104 Fahrenheit, 103, 102 and a half, 102, 101. Now, of course, some of the heat is going into the water bath, and then some is being carried away by the surrounding air by thermal convection. So we're getting some of the heat into the water bath, but not all of it. The water bath will be heating up a little bit, but it's also itself cooling down because of thermal conduction in the air, and also probably a little bit of evaporative cooling. So now we're at 98 Fahrenheit, and this clock is reading. I'm looking at about, right now I see a time mark coming up at 10. It's going to be, looks like 9:54, coming up on 9:54 p.m. out here in Palm Springs. The camera also has a digital clock, and it's reading 6:35, 6 minutes and 35 seconds since we started the video. What's our temperature now? 95. So we all have seen this going, but what you could do if you wanted to take the data, you can read it off the digital dial for the temperature and off the analog display for the clock, you could plot temperature versus time. So you have a plot with the y-axis as the temperature in Fahrenheit and the x-axis as the time in time elapsed from when we started the experiment in hours, minutes, and seconds. Now we're 93 Fahrenheit. Now, if you wanted to, you could turn that graph on its side, and then you would have a plot of time on the y-axis and temperature on the x-axis. So time and temperature are obeying a functional relationship. Now, when the coffee cup approaches when the coffee cup approaches equilibrium, the temperature is slowing its rate of change. The time derivative of the temperature is going towards zero. So when the coffee cup assumes room temperature was around 74 degrees Fahrenheit, 72 degrees Fahrenheit, then it will no longer evolve. And so in a thermodynamic sense, time is stopping for the sample in the coffee cup. No more thermodynamic, no more motion in the thermodynamic state space. It settles down to a constant temperature. So in a sense, when you're in thermodynamic equilibrium, when the sample is in thermodynamic equilibrium, time has stopped for it in a thermodynamic sense, and you have a steady equilibrium state of constant, unchanging temperature. Now, of course, this coffee cup is in thermal contact with the atmosphere and the countertop underneath and so on, and the thermocouple itself. So if the outside conditions change, then of course the temperature of the sample in the coffee cup will change. Okay. So one of the really surprisingly profound things about simple thermodynamics is that it is giving you a direction in the future. And that's very profound. So a lot of, the laws of physics, Newtonian physics for instance, they are all time reversible. If you reverse the sign of the time variable in Newton's equations of motion, the equations are, they're the same. There's another interesting thing about thermodynamics, since we have time here. If you described all the molecules in the coffee cup, in the liquid sample in there, by Newtonian mechanics, we probably have about 10 to the 22, let me see here, per cubic centimeter. Well, we have something on the order of a 10 to the 23rd molecules, let's say. And the phase space, the state space for particles, is that every particle has a position and a momentum in 3 dimensions. So each particle has 6 degrees of freedom if you're just looking at its motion. And so the phase space to describe the location of every particle would be 6 times the number of particles. So you have this huge phase space of 6 times 10 to the 23rd dimensions. You locate the particle in its momentum and position space, and you need 6 coordinates for every particle. So each particle is sitting in a 6-dimensional phase space, and we have all this 10 to the 23rd particles times 6, so this is this huge dimensional, high dimensional phase space. And yet in thermodynamic equilibrium we really just need temperature, volume, density, pressure. So you can describe the liquid in a very low dimensional space. The temperature evolution is kind of slowing down here as we're getting closer to room temperature. What do you think the curve will look like if you plotted it up versus time? Would it be a kind of a decreasing exponential curve, like something like e to the minus alpha t? If the process of heat transfer is diffusive, then by conduction, diffusion of heat through the material into the colder water bath, then the time dependence of the diffusion equation gives you e to the minus alpha t for the situation. So it should obey pretty good approximation, an exponential decaying temperature converging to room temperature if you go out to infinite time. Now that's an interesting point. How long does it take to really reach thermodynamic equilibrium? If you really had a super duper temperature monitor that had 10 significant digits, then you would be able to detect the last few millidegrees as you approached equilibrium. And so the closer, the more accurate your temperature measurement, the more time it takes to reach equilibrium. And you could speed up the equilibration process if you wanted to. For instance, we could well, how would you do that? In this setup, one way you could do it is to use a metal coffee cup instead of a ceramic one, so it would have better heat conduction, and so the experiment would go faster. Notice the coffee cup itself was pretty hot when I pulled it out of the microwave. It had heated up because it was in contact with the liquid. Microwaves didn't really heat the cup up that much, but the hot coffee inside is warming up the cup. So if you had a good metal coffee cup, then this might go faster. On the other hand, if you had a vacuum flask, a thermos bottle full of coffee, you'd be waiting for days before the temperature came down. So the rate of equilibration is dependent on the quality of the heat conduction between the sample and the heat bath. Now, in an ideal thermodynamic experiment, you might have a very large heat bath, so that or a heat bath that had a thermal regulator in it, so that it kept a constant temperature. That would be a little fancier apparatus that you might find in a chem lab. We're down at 82 Fahrenheit. Let's see how close that is. I'm going to just pull this out and see what the water bath is doing here. It's probably a little bit hotter than room temperature. Let's see, we had, okay, so water, yeah, see it's 78 there. Water, I'm kind of touching the coffee cup a little bit, but 78. Now if I pull it out of the water bath, we'll get room temperature now. Let's see what room temperature is. Just put it down here. Yeah, see, you're coming down here to 72, 73, 72 degrees Fahrenheit, which is a good room temperature. Out here in Palm Springs, of course, we're experts on thermal transport and cooling, because in the summer it gets so hot outside that to be comfortable, you have to have really good air conditioning and good air circulation. So I'm reading 71 Fahrenheit here outside the water bath. Let's check back inside now. So it jumps up to 78, 77, 78. And then our coffee is still probably in the 80s. Let's see what's inside there. Yeah, there we go. Well, it's just sitting now about, looks like about 80 or so. Well, that's pretty close. It's converging to equilibrium. And this little experiment just shows you the arrow of time. Now, there's one other experiment we can do here. You may notice over on the left I have a infrared temperature sensor from Fluke. This is a nifty little gun. The HVAC people use this to measure the temperature. It has a digital readout, and you can measure temperature by pulling the trigger here. So let's see if we can get a temperature reading. All right. Okay, so right now let's put the laser point down there on the ground, on the bottom. So it's a little hard to read here. Let's see if I, okay, here we go. Okay, so that's why it's an HVAC Pro device. A good HVAC technician will have one of those and know how to use it to find heat leaks. Okay, I hope you enjoyed this little home experiment, and we'll get back to the subject of manifolds for thermodynamics and the laws of thermodynamics in differential form in the local space of the local linear space